Okay, so up till now, we have been talking about strong acids and strong bases, which pretty much break up 100%. They give up their H or they accept H's 100% of the time. All right, now that, of course, they're easy calculations. You know, we can calculate the pH, the hydronium, the hydroxide fairly easily. What we have to use for these guys, for weak acid and weak bases, is another equilibrium constant. But I've got to derive it. He's got a new name. He's called Ka, because these guys only slightly ionize in solution. I'm going to derive this new equilibrium constant for you today. I'm going to shorten that derivation up. You saw how long the derivation took for Kc, for Kp, and even for Kw. All right, I'm going to shorten it up. I'm not going to go through the stuff that I've already shown you at least twice by now. The derivation of Ka assumes you know how to get from point A to point B, and then I'm going to go from point B on to infinity and beyond. Buzz Lightyear. Okay, so here, let's assume we have a weak acid of the formula HA. HA plus water yields hydronium and whatever the negative ion is. Now that HA could be a binary acid like HF. HF, I told you before, is a weak acid, hydrofluoric acid. Very, very small Ka. It could be a polyatomic ion, right? A nitrate or a chlorate. Well, if it's a nitrate, it would be a strong acid, nitric acid. But you know what I mean. Any kind of the polyatomic ions. It could be on here as well. But either way, whatever that negative ion, and one of the big ones we're going to be learning about is the one Maddie asked about the other day. It looked like CH3COOH, I believe. You asked or Sam asked about that. That guy's another example. He's called acetic acid. We're going to be seeing him a lot. Anyway, that's a generic formula for any weak acid. You can get it, I would imagine, from there to here if I were deriving it. First thing you would have done is you would have said, well, the rate forward would equal these two guys, assuming a one-step mechanism. The rate reverse would equal these two guys, raised to their coefficients times their Kf. Rearranging, blah, 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 you'd come up with this. We've done it before a couple of times, even getting Kw. Now, here is the deal. If you're talking about a very weak solution, a dilute solution of a weak acid, once again, as we saw with Kw, water is constant. It doesn't change. Okay? Why? Think about it. It's a dilute solution, so I didn't add much. By definition, I added very little of this. On top of that, very little of this, by definition, if it's a weak acid, doesn't break up. So the amount of water, when I'm subtracting from water, the X that I'm subtracting from water is incredibly small. So I don't really have to, in dilute solutions, worry about water. I bring him over with the other constants. Now, in the Kw derivation, you had water and water both on the bottom. Here I've got HA and water. It doesn't get rid of the entire denominator, but it does look like this. Kc, the equilibrium constant times water, would look like the hydronium and then the negative ion over the HA. You're going to be using this equation, which of course that's Ka. You're going to be using that equation for the rest of the chapter. That's pretty much what we'll be using for the rest of the chapter to solve all of our problems. But what I wanted to add to this, I pretty much did this with, in the previous video. The reason I'm redoing this one is for this reason I'm about to get to in a second. First off, though, before I get to the new thing, I want to make sure I summarize something about Ka. We should know what Ka's size means, okay? If Ka is very small, and if it's a weak acid, I think by definition it's going to be very small, right? Because weak acids don't break up very much. If Ka is very small, it means most of the HA stood over here and didn't become hydronium ions, okay? If Ka is very large, then it probably wouldn't be a weak acid, but the larger the Ka, I could say something else the other day. I said about conjugate acids and bases. I just gave you the definition and what they are. Now, I'm going to get to something down here in a second, so don't copy anything I'm about to do here. The next thing I'm going to write here is going to go right into those notes. But I want to back up and show you something. If I were to say that this guy's clearly the acid in this case, right? All right. This guy's the acid. You all agree that he's acting as an acid. Some of you are experts at acting like acids. Don't like that one. You can get his little red ball. Already did when I turned around. Very good. Excellent. Oh, it's still there? How did it move? How did it move? Like it's like a ghost. Anyway, so there's my acid. Anyway, there's my acid. Now, you agree he's an acid because he's donating an H. All okay with that. Well, what must this guy be like? According to whether he's a conjugate, what is he? He's the conjugate base. All right, so let me show you what would happen if he's the conjugate base. This is really kind of interesting. I watched this video today, and I thought, this is kind of really explains something that I always just use this equation. The equation's on your sheet, and you will have to use it. But this shows you where it comes from. Does everybody agree if he's the acid, he's the conjugate base? Let's write underneath, not you, just me, underneath this. If you say a conjugate, if you take any base and you add water to it, this is kind of fun. You agree that if I take my base and I add water to him, what does a base do? He accepts H. And of course, he'd have to accept that from the water. So I would get, if he lost his H, he would now be an OH, and he would be an HA. Huh. Ha. 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 That's crazy. Now, the funny part is, do you remember Hess's law? Remember Hess's law? Can I cross anything out here? Is anybody going to cross out? Ha is on the left. Ha is on the right. Yeah, A is on the left. A is on the right. Huh. Huh. So what do I end up having here? I have H2O plus H2O, because there's two of them still here, right? Yields what? Yeah, have we seen that before? Yeah. Isn't that cool? And yeah, thank you. I didn't really create that, but I thought that was kind of cool. But this explains something. This explains why Kw, we all know Kw because hydronium says hydroxide, but guess what else Kw equals? Kw is going to equal Ka times Kb. Wow. Mind blown. I know. That's so cool. All right, so let's get down to the rest of the notes you got it right here. Right, watch. Here's where we left off. All right, Ka not only equals that, okay? Kw equals Ka times Kb. And I want to explain how those are all going to be related. There's one more thing you're going to write underneath that, which I actually don't have written there, but I'm going to write it just in pen. What's that? Okay. So if Kw equals Ka times Kb, remember a minute ago I was talking about the size of Ka. You guys all know what Kw is. What's the actual numerical value for Kw?
1 times 10 to the 14.
So everybody agrees that Kw, and don't write this here. I've actually realized there's no room on here left on here. I'll back it up a second. We all know Kw is 1 times 10 to the negative 14, correct? Now hold on, watch. So if my Ka, for example, were 1 times 10 to the negative 4th, what will my Kb have to be? Negative 1 times 10 to the negative 10th. In other words, the stronger the acid, the more he wants to go this way, the less that other guy is going to want to get water, his H back. The conjugate base is going to be. You see, that kind of all makes sense. Now, I'm going to go one step beyond this because we're going to become very important. We did pH for a reason. I told you a guy who invented the pH scale worked at a bottling plant. He wanted to just keep track of acidity, and he just found it easier to write down the negative exponent of 10. Because it's just writing down pH of 2, 2.5, whatever. It's a lot faster than writing down 0.00002 or 2 times 10 to the negative whatever. A lot of times, instead of using Ka and Kb and Kw, guess what they use? pKa and pKb and pKw. So that you all agree that 1 times 10 to the negative 14th is Kw. Ka, well, what do you think P, and this you can actually write down underneath. I don't have any more room down there. pKa plus pKb is going to have to equal what number? 14. It's just the power of 10. You see? And that's why if in a problem they give you the Ka, you can figure out the Kb. If they give you the pKa, you can figure out the pKb. You can work those all backwards. It's all interrelated. And you say, so why do they have to make it so complicated? I mean, it's bad enough we could have just done all this by just doing simple KC. All right, the reason is mostly due to convenience. Most of the time, it's due to just the convenience. We don't like to write down useless information, unnecessary information. All right, so anyway, the point is whether you agree with the idea of making pKa's and pKb's and using them and being able to see them and seeing how big their size affects how much acid you're going to break up in solution. You have to do it, whether you like doing it or not. So we're going to have lots of problems with that as well. And there's another equation called the Henderson-Hasselbalch equation, which again summarizes and brings everything together. We derived that one. You're not going to like that either. All right, so anyway, your homework tonight I have, I think, on the board here. Hold on. Yeah, right there. 30 and 31 is all we have that's new on this stuff. We're going to take this to the next level tomorrow and do calculations with it. Okay, so tomorrow we'll be doing some more. Tomorrow I'm also checking that homework. Okay, so.